As we continue our treatment of the electric force, I'd like to develop the idea of electric potential energy. So first, I think it would probably be helpful to just have a quick bit of review. And let's just remember doing this for gravity. So just real quick here, I'd like you to imagine a situation here where I've got a rock. It's just sitting there, initial speed 0. It's saying some height h above the ground. And what I want to know is if I let the rock go, just before impact, so I would like to know what is V final equal to. We know the rock's going to pick up speed until just before it hits the ground. So go ahead, just pause the video for a moment. Go ahead, set that up, solve it, and get back with me and I'll share my solution. Okay, so the way I would be doing this here is I would be going ahead and defining where should I put y equals 0. Makes sense to put at the bottom of the problem. It'll keep all my potential energies positive. We'll say that this point here is y equals h. And then you can just make a table of energies. So final, initial, like this. And you list all the kinds of energy you can think of, which in this case is going to be kinetic and gravitational potential energy. Okay, so initially the object was dropped from rest, so its kinetic energy is 0. At the end, it's going to be 1/2 mv final squared. And then at the end, because I put y equals 0 at the bottom, that makes the potential energy 0 there. And the initial potential energy will be mg times the y coordinate up here, which is h. So mg h. Now what you do is just add up the columns and equate. So 1/2 mv final squared equals mgh. Cancel the m's, which is good because we didn't know what m was going to be. And we get that v final is the square root of 2gh. Now you could have totally done this by finding the force of gravity on the rock, using that to find the acceleration, and then doing a kinematics treatment. You'll get exactly the same answer. But this gets us to recalling what the pros and cons of energy analysis were. The single biggest pro for doing energy analysis was that it's easy to do, at least comparatively speaking. Versus the way we would have to do this the other way, you had to use Newton's second law, and to get the acceleration, put that into kinematics. Okay, it's not awful, but this is faster. And generally speaking, if a problem lends itself to energy analysis, you can pretty much rip through the problem like a hot chainsaw through butter. Now the downsides, the two downsides are we give up path information. So if we need to find the actual trajectory that an object takes, we're going to have to use something else. Either we're going to have to actually go ahead and find the forces and do the kinematics or whatever, or sometimes we can get lucky and exploit a constraint. For instance, if you remember when we do this sort of problem, say with a roller coaster or something like that, you knew the trajectory of the roller coaster. It was the track, or at least you hope it's the track. Otherwise, you'd be in real trouble. So that's the well, one of the downsides is that we don't know the path information, so that if we need that, that's important. And we'll have to do it some other way. The other downside is we also give up time evolution information. And what this means is that there's nothing that we can do with energy analysis to find out, say, how long it took the rock to fall this height, h. So if that was important to us, we'd have to do forces and kinematics again. And so those are the limitations. But a lot of times we don't need those, or we know them already, like the path is the track or something like that. In which case, if a problem lends itself to energy analysis, we'd like to go there because it's a lot easier to do. Now, we also recall that we could only do energy analysis if forces were conservative, or at the very least if we had non-conservative forces, that they were the kind that never did any work. So the big question here is, just as a quick pause and ponder, is the electric force a conservative force? Go ahead and pause the video and get back with me on that. And the answer is yes, it is a conservative force. So the electric force is conservative. And fortunately, unlike what we had to do before to conserve the tip, before, when we had to think about this with gravity, we had to do an awful lot of work to prove that it was conservative, which, remember, means that the energy, that the work done by the force only depends on the endpoints and doesn't depend on the exact path you took to get to the endpoints. And generally, that can be a bit of a chore. But here we actually get a little lucky. The deal here is that we've already shown that gravity is conservative. And just as a quick recall, the force of gravity was G m1 m2 over r squared. This is Newton's law of universal gravitation. Now, if we go and take a look at the electric force, if we go ahead and write down Coulomb's law, so the electric force is K Q1 Q2 over r squared. We see that they have the same mathematical form. So what does that mean for us? Since they have the same mathematical form, literally all the arguments that we did before to prove that gravity was a conservative force, literally all those same arguments, when applied to the electric force, will give the exact same answer because they have the same mathematical form. It just depends on, in the case of gravity, it depends on the masses. In the case of the electric force, it depends on the charges of the two players involved. And it's just the square of the separation. And the forces are directed along lines that connect the two objects involved. So because of that, it turns out that the arguments are exactly the same. So what this means is we can kind of cheat a bit, and we can remember that we determined that the best way to write the gravitational potential energy function in general, so again, this is if we were talking like just looking at two individual masses, the MGH thing was a excellent approximation we could use near the surface of a planet. It was minus G m1 m2 over r, where r is the separation between them. And remember, we were always free to choose to within a constant what our potential energy functions were. And so it turns out that for reasons that have to do with the calculus it takes to derive this stuff, it made the most sense for us to say that the gravitational potential energy, if our two objects were infinitely separated, was set equal to 0. With that choice, we said that the gravitational potential energy was this. So with the electric force, we can do the exact same analog. We will demand that the electric potential energy be 0 at infinite separation. The little circle over the equal sign means set equal to. And you could do it for other things, but again, the calculus arguments that are used to, calculus-based arguments that are used to get these answers work most cleanly when this choice gets made. And so the electric potential energy is plus K Q1 Q2 over R. Now, at this point, you might be going, wait a minute. We had the exact same functional form here. So why does gravity get a minus sign and the electric force get a plus sign if the forces look basically the same? So go ahead and pause the video and think about why we would have a different plus and minus sign between these two, and then I'll get back with you on that. So there are two different ways that we can think about this plus and minus sign, so I'll take them in turn. One thing that I didn't say is that here I just wrote what the magnitude of the forces were. However, if we have two positive masses, and I don't know what it would even mean to have a negative mass, if I have two positive masses, which way is gravity going to work? It's going to try to attract the two objects. So let's say if I have two positive electric charges, which way is the electric force going to work? Yeah, it's going to work to repel the two objects. So here, this is attracting, and here for both positive or both negative charges, it would repel. Now, if there's one positive, one negative, it attracts. But the point is that we wind up having a difference in direction for what the natural behavior would be. Say here, two positive masses, you attract, two positive charges, you repel. When you take that into account, that forces you to have the opposite sign for the electric version of this than for the gravitational version of this. So another way to think about this would be to think about what the spontaneous behavior would be like. So just ask yourself, if I go and take two objects that are interacting gravitationally and I let them go, they're going to want to get closer together. If you're going in the direction of spontaneous behavior, that would be a decrease in potential energy. Well, what's the spontaneous behavior going to be like in the case of the electric force? Well, if I have two positive charges and I let them go, you're going to want to go to a lower potential energy by flying apart. So here, we're going to get to a lower gravitational potential energy if R gets smaller. You get closer together, you'll have a bigger negative number, which is lower than the negative number you had before. Here, if I have two charges and I let them fly apart, R gets bigger. Two positive charges and R, let them fly apart, R gets bigger. So I start with a big positive potential energy, and now I am spontaneously have moved to a lower potential energy. Same would be true if they're both negative charges, but let's look at the case that one's plus, one's minus. If one's plus, one's minus, you would want them to attract. Well, if one's plus, one's minus, that's going to make this all negative. Everything else in here is positive. That's going to give us a negative number. So then it's the same kind of deal as here. If we go in the direction of spontaneous behavior, I'll go from some negative number, and as R gets smaller, that will make this a bigger negative number, which is a lower energy state. So we get the spontaneous behavior that we want for all possible combinations of charges if we have the plus sign. So you can think about it either way. Either you can say, hey, this naturally wants to attract two like-signed masses. They can only be positive, but just work with me here. Similarly here, if I have two positive charges, they want to repel. That's a difference in direction, which gives us a difference in sign. Or you can think in terms of the spontaneous behavior. All right, let's try to make this a little concrete by thinking about a process that happens all the time inside the sun. The way the sun produces its energy is through a process called the proton-proton chain. That's something we don't have to worry ourselves about too much at the moment, but one thing that will happen during all the nuclear fusion processes in the core of the sun, especially as the sun gets older, the proton-proton chain made a bunch of helium particles. Now, as we get more and more helium nuclei built up, eventually they're going to want, we may run into the possibility that they'll try to fuse together. Now, the special name we give for a helium nucleus, we call that an alpha particle. And let's just say that I have two alpha particles in the interior of the sun, and let's just say that they're both going at 1 million meters per second. And they're on a straight-on collision course towards each other. Now the question is will they get close enough together so that we will end up having a nuclear fusion occur? For that to happen, their distance of closest approach is going to have to be on the order of 2 femtometers or less. So the femto prefix means 10 to the negative 15. So if it turns out that their closest approach distance is less than 2 femtometers, we will get in the range of the strong nuclear force. The strong nuclear force will pull them together. Nuclear fusion will occur. And this will release some energy and make a heavier nucleus in the process. So let's go ahead and figure out what this distance x is at closest approach. All right, so we can play exactly the same kind of game we did before. We make our table of energies. So we just say final, initial, kinetic, potential. So our final kinetic energy, I'm sorry here, I forgot to mention, we are starting at this distance of very far apart. I mean, heck, even a few centimeters is very far apart compared to femtometers. So we'll say that this is roughly infinity. So since this is roughly, so our final kinetic energy at closest approach, we would be going at a speed of 0. So kinetic energy is 0. The initial kinetic energy, well, one of these will have a kinetic energy of 1/2 mv squared, the initial squared. So will the other one. Okay. My initial potential energy is going to be basically 0, because I said these are very far apart, so we're calling that infinity. And at infinite separation, the potential energy is 0. All right. So at closest approach, it's going to be K times the charge of one alpha particle. An alpha particle has a charge of plus 2e because it's made of 2 protons and 2 neutrons. The neutrons don't contribute any charge, the protons do. So this will be K times 2e times 2e over my separation x. Great. So let's go ahead and equate, and we'll try to clean up the math just a little bit while we're at it. So this is going to be 4ke squared over x, just 2 times 2 is 4, e squared. And then half plus a half is 1, so this will be equal to mv initial squared. All right, little bit of a cross multiplication action is going to give us that our closest approach is 4ke squared over the mass of an alpha particle times v initial squared. Now the mass of an alpha particle, very roughly, to three figures, both a proton and neutron are not that far off from 1.67 times 10 to the negative 27 kilograms. So we can just say the mass of an alpha particle is roughly 4 of those. So let's go ahead and substitute away. So 4 times 9 times 10 to the 9 Newton meters squared per Coulomb squared. E is 1.6 times 10 to the negative 19 coulombs. We'll be squaring that over my mass of 4 times 1.67 times 10 to the negative 27 kilograms. And initially we're going at a million meters per second, so 1 times 10 to the 6 meters per second, and we square that. All right, grind all of that through your calculator. You get that if they were head-on to each other, their closest approach would be 1.38 times 10 to the negative 13 meters, or pop the decimal point 2 over, we would be getting 138 femtometers. This is still quite a bit bigger than the roughly 2 femtometers we need for the strong nuclear force. So what will happen is they'll get to within 138 femtometers of each other, and then they'll repel and start flying away from each other. Now, if they're going fast enough, just due to thermal energy distribution in the sun, if they happen to be going fast enough that they got to within 2 femtometers, then the strong nuclear force would kick in, and the nuclei would get sucked in together, and nuclear fusion would occur. All right, so again, working in analogy to gravity, you remember that in a uniform gravitational field, i.e. near the surface of the Earth, we said that the potential energy could be written as mgy, where that's the y coordinate. We can do something similar here, although we have to be a little careful thinking about what's higher and what's lower. So dimensioning your coordinates gets to be just, you need to take a little care. So here's a so let's say you're in a uniform electric field. So let's say I have 2 points I'm interested in. So my example here, I'm going to imagine I'll have a positive charge here that's going to work its way over to here. So first off, since this is a positive charge, which way is it going to feel an electric force? Go ahead and think about that for a second. Yeah, it's going to feel force to the right because the electric force is the charge times the electric field at that location. The electric field points to the right, the charge is positive, the force is to the right. So this means that this charge wants to go from left to right. So this means that this is going to be a higher electric potential energy, and this will be a lower one. And we're free to even just say, let's just make this one 0. By an argument similar to what we did coming up with the mgy thing for gravity, in that case here, the electric potential energy will be Q times E times the x coordinate here. So this distance here, let me mark that off in a different color. This distance here away from my u equals 0, that is my distance x. This is a positive, so this is the positive direction I'm kind of thinking of here for dimensioning my x. The electric potential energy here would be QEX, similar to doing mgy for gravity. So let's just go ahead and do a case of this with some numbers just to make it a little more concrete. So let's say that for this example here, the charge was a plus 4 microcoulomb charge. Let's say the mass of this thing is a gram. And let's say that our total distance we're going to travel here is 1 centimeter. Alrighty then. So if we started initially at rest, what we want to know is how fast is it going after it travels that centimeter. Alright, let's give it a shot. So again, same deal. We set up our table of energies here. So we'll say final, initial, kinetic, electric potential energy. So my final kinetic energy is going to be 1/2 mv squared. My initial is 0 because it's at rest. So 1/2 mv final squared, in fact. My final potential energy is 0 because I set it to be 0 there. So my initial is QEX. Okay, again, same deal. Go ahead and equate these. 1/2 mv final squared equals QEX. So rearrange, do some algebra. V final will be the square root of 2QEX over m. And now let's stick in the numbers. So this will be square root of 2 times 4 times 10 to the negative 6 coulombs, because micro means 10 to the negative 6. I said it was a 2,000 Newton per coulomb electric field, 0.01 meters. I did say that, right? No, I did not say that. My apologies. This is a 2,000 Newton per coulomb field. And then a 1 gram mass is 0.001 kilograms. All right. So grind that all through, you will get 0.4 meters per second. So 40 centimeters per second. That's pretty darn respectable that after traveling just 1 centimeter in a pretty decent, reasonable size electric field, nothing too crazy, we're already going 40 centimeters a second. The electric force gives us some zip here. Alrighty, so in the next video, we're going to be introducing the idea of electric potential, which, despite its insanely similar sounding name to electric potential energy, is a different but related idea. And we'll get into why the unfortunate naming and all that in the next video, so we'll catch you over there.